If there was an eternal universe, does that negate the theory of the Big Bang? Or, do we say the universe began 13.8 billion years ago? Actually, we know. What if the universe we live in isn't the only one? What if there are other universes where things are different? Some scientists believe there are an infinite number of universes, and those multiverses can be broken down into smaller pieces called bubbles, each one existing on its own with different laws of physics and properties. We believe, though we cannot yet prove, that our multiverse of universes is 11-dimensional. So think of this 11-dimensional arena, and in this arena, there are bubbles. Bubbles that float, and the skin of the bubble represents an entire universe. So, we're like flies trapped on fly paper, we're on the skin of a bubble. It's a 3-dimensional bubble, the 3-dimensional bubble is expanding, and that's called the Big Bang Theory. So are we really living in a huge bubble, and is the Big Bang Theory wrong? Join us as we dig into the bubble multiverse theory as well as which scientific experiments have been performed to test it. A persistent cosmological puzzle has been troubling physicists since 1917. What is the universe made of? Complicating this already mind-boggling question is the fact that our best theories conflict with our observations of the universe. Albert Einstein, according to scientific folklore, felt a unique responsibility for introducing this entire problem, reportedly referring to it as his biggest blunder. Essentially, Einstein's novel theory of general relativity didn't hold up when used to describe the universe as a whole. General relativity described the geometry of spacetime as being a trampoline-like surface. Planets are heavy bowling balls that distort the surface, creating curves. If a less heavy ball like a marble was placed near the bowling ball, it would roll along the surface, just like the motion of planets in orbit. Thus, orbits are explained not by a gravitational force, but by curvature in spacetime. This proposal worked when considering small regions of spacetime, but when Einstein applied it to the entire universe, its predictions didn't fit. So, Einstein introduced the cosmological constant, a fixed value that represents a kind of anti-gravity, anti-mass, and anti-energy counteracting gravity's effects. But when scientists discovered that the universe was expanding rather than static as Einstein had believed, the cosmological constant was set to 0 and more or less ignored. After we learned that the universe's expansion is accelerating, however, scientists could no longer conveniently cancel out Einstein's anti-gravity suggestion. What was previously assumed to be empty space in the universe now had to be filled with huge amounts of mysterious anti-energy to explain observations of the universe's ever-quickening expansion. Even so, observations of the universe's expansion suggest that the energy is 60 to 120 orders of magnitude lower than what recent quantum field theory predicts. What this means is that all of this extra energy is somehow missing when we look at the universe as a whole. Either it's effectively hidden or very different in nature to the energy we do know about. Today, theoretical physicists are trying to reconcile these mysteries by examining the structure of so-called spacetime in the universe at the smallest possible scale. With surprising findings, spacetime might not be the trampoline-like plane scientists once envisioned, it might be a foamy mess of bubbles all containing many universes, living and dying inside our own. To try and solve the mystery of what fills the universe, scientists have been exploring the possibility that it's actually full of bubbles. The quantum foam theory has been around since 1955 when physicist John Wheeler came up with it, but it's seeing a resurgence in 2019. Modern researchers suggest we may be closing in on the technology we'll need to actually observe and measure dark energy, or whatever the universe is made of. The spacetime foam explanation for dark energy basically says that the space in between conventional matter is occupied by bubbles that work like dark matter. They keep the classical matter and energy in the universe from becoming ubiquitous, at least theoretically. What's astonishing is that, according to the research, these bubbles have their own continuum, their self-contained universes. Time doesn't have to work the same way inside these bubbles because, for the purposes of this theory, and due to a concept called entropy, the arrow of time isn't necessary to explain the quantum world. If you were a subatomic piece of dark matter caught in a spacetime foam bubble, you might experience time backward, sideways, or not at all. The dark energy would have to work apart from our classical model of thermodynamics while simultaneously accepting the parts of it we consider immutable. Space-time foam theoretically accomplishes this. It's a potential piece of evidence towards a grand theory of everything. If that doesn't boggle your mind, consider this: if space-time foam is real and scientists can prove it exists, such knowledge would force us to consider that our own universe may be nothing more than a tiny bubble in someone else's universe that could pop at any moment. That reminds us of the concept of a multiverse. We currently do not have a solid understanding of the earliest moments of the Big Bang. We know the general outline: our universe was once much smaller and hotter in the past. Nowadays, it's not so small, and it's a whole lot colder. We've tested this basic idea against a variety of experiments too, but as we rewind the clock to the Big Bang, we reach a scale where our physics simply breaks down. When the universe was less than a second old, the conditions of the cosmos were so extreme that we have no theory of physics to guide us. That said, we do suspect that in its earliest moments, the universe underwent a radical transformation event known as inflation. It appears from all available evidence that when our cosmos was only a fraction of a second old, it rapidly expanded to enormous proportions, growing by at least a factor of 10 to the power of 60. This inflationary event set the stage for the remainder of the Big Bang, when our universe flooded with particles and radiation that would then grow up to become galaxies, stars, and planets. Here's where we get a multiverse. Maybe inflation never ended. Maybe the entire universe is constantly undergoing this out-of-control, rapid expansion, but pieces of it branch off and settle down into something more sedate. Thus, what we call the universe is just a tiny bubble of the true ever-inflating, ever-expanding huge universe. In this view of inflation, the entire universe never stops inflating, it just keeps getting bigger at an accelerated pace, faster even than the speed of light. What triggers a patch to slow down and pinch off is merely a random quantum fluctuation. Our patch of the universe just happened to randomly stop inflating compared to the larger universe, but the rest of the universe outside our bubble continues to do what it was doing before and what it will always do. Our patch is not alone. Different patches can also randomly settle down and become a normal, calmly expanding universe. To observers in any of those patches, they will see a Big Bang in their past, just like we do. They will have a cosmos filled with matter and radiation just like we do, and they will have a limit to what they can observe, just like we do. In this never-ending inflation scenario, each of these patches or bubbles or pockets or whatever metaphor makes the most sense to you appears as its